We're going to make a video about this little wonder. This is a LED street light. It's a broken LED street light. Here's the aluminum cover that goes right over this area, and it's broken, so it's not any more use. And I managed to get it because it's broken, and hey, just thought I'd play with it. A couple neat things. One, LED street light is going to put out a pretty intense light. You might find it useful at some point for something. Well, I think it's maybe even neater is each one of these light bars, there's 6 light bars in this thing, and each one of them can be taken out separately apparently. They each are wired separately. We might find a good use for those individual light bars, as well as maybe making use of it in its entirety. So, just thought I'd share with you how to convert this street light into something useful at the house. Whether you use them as individual light bars or as a whole, it might change the electrical design slightly, but the design we're going to use would work no matter whether you used one or all 6. I just sized it so it'll fit all 6, which means it'll readily fit any one light bar as well. So let's go play, see what we can come up with, see what we can learn about this LED light. Well, let's start off and talk about what we found when we opened up the light. There was a bunch of electronics in it, which, if you saw the light just now in that metal cover area, there's no electronics but a few wires coming out of the lights. This is the main thing I guess we found. There was a number of other circuit protection devices and I think surge stabilizers, things like that. But there were 2 of these in there. It was actually controlled in 2 banks, 3 and 3, 3 light bars in each bank. So there's 2 of these wonders. And if you notice, I'm not sure, hopefully you can read this. It says right down here that this is an LED electronic driver. Don't confuse this with a fluorescent ballast. It has a similar appearance and structure to a ballast, but this is far from a ballast. But this is basically a transformer and rectifier, which is converting AC voltage into DC voltage of a certain range. So let's look. I'm not sure if you'll be able to make this out on the video, but basically the voltage in is 347 to 480 volts AC. And it is a single phase. It's not 3-phase like typical 480. You're just taking one leg of the 480. The frequency 50 to 60 hertz. The input's 0.5 to 0.35 amps, depending upon which voltage input you're using for this thing. And it says right there too, 347 volts to 480 volts. So we don't have 347 to 480 in our house, and so right off the bat I just started stripping out these electronics, knowing we were going to have to go with a different circuitry. And so let's talk about what the output of this device is. That's what we want to try to match. And it says right here, the amperage out, I out, is 0.7 amps DC. The voltage out is 60 to 210 volts DC. And then the max volts out is 250 volts DC. And the max amperage is 0.76 amps DC. So basically we need to take, if we want to do this on house current, we need to take our house current, which here in the US is 60 hertz, 110 to 120 volts for single phase, and we want to take that and convert it to something that this thing can use, which 120 volts DC or around there, more than that even's fine. And the amperage load per bank is about 0.7, so that's a 1.4 amp overall draw. So we did some calculations, we started designing a circuit, and I'll show you that that design and a little background on developing that circuit. Alright, so let's start our circuit design. We're going to be using household current, which in the US comes in at 60 hertz and comes in at 120 volts. AC. Now when we measure voltage with a typical voltmeter, we're measuring what's called the root mean square voltage, the RMS voltage. So the actual voltage at peak on that curve is 170 volts AC. If you want to confirm that for your system, depending on what volts you have coming into 20, 240, 120, just multiply your initial RMS voltage by the square root of 2, which is 1.40 something something something. Anyway, that'll give you 170 volts in this case, 120 volt RMS. Actual peak voltage is 170 volts AC, so who cares? We don't normally deal with that. Why do we care in this case? Because whenever we rectify this AC voltage to DC, it's going to come in at 170 volts or very near it based on voltage drop across other pieces of equipment. So it's relevant to know what that peak voltage is in this case. So let's talk a minute about just AC current and what we're trying to do. So this is basically just a sine wave, the blue curve, and if you look at the red dotted line, that's actually your RMS voltage, which is more or less a weighted average, and it's not quite, by the way, but unless you want to go study up on root mean square, just take my word for it. That 120 is what we measure when we stick a multimeter probe up in there, but this is the actual wave, and it tops out about 170. So what we're going to do with the rectifiers, we're basically going to take, in mathematical terms, we're going to take the absolute value of this wave. So anything that's positive will remain positive. Anything that's negative, this downward leg here on this downward phase, negative phase, is going to be flipped positive. So whenever we get the rectifier in the circuit, it's going to look like that. It's going to be two positive waves, and if you'll notice the frequency here, which is start to finish, is 60 hertz. The frequency that we'll have here, start to finish, is going to be 120 hertz, twice this cycle, because we're just simply taking the absolute value of that negative portion of the sine wave. So this is what we're going to do now. The downside to this is, if you look at it, it's DC, as in it's not negative. It's direct current, but it's because it's not negative, but it's hardly ripple free, is it? It's got a huge ripple, around 170 volt peak to peak ripple, and well, that's not really ideal for what we're trying to do. So we're going to use capacitance in our favor, and we're going to stabilize this ripple, and we're going to go through some calculations on how to do that. So this is our inlet, 120 volts, 170 volts RMS, 170 volts peak, and 60 hertz. Now when we go to our rectifier, first let's look at our rectifier. You can go and buy 4 diodes, the right voltage and amperage rating, or you can buy one of these little wonders. This is a full bridge rectifier. It has 4 pins. 2 of those pins, the center 2 pins, are for your alternating current, and in the outer 2 pins are your DC output. The one with the angle corner here, this is positive DC, and this is negative DC. So this is what we're going to use. In lieu of going and buying diodes and wiring them up, we'll just simply wire to this full bridge rectifier, which internally is just 4 diodes in a full bridge configuration. And then also we're going to use capacitors, as I indicated. These I happen to have. Note this points to the negative leg, this one right here, and this is the positive leg. But these are, if you can read it, is it upside down? It is. These are 1,000 microfarad, 300 volt capacitors, and we'll show you how we're going to deal with those here in a minute. So when we go into our rectifier, first things first, there's a voltage drop across that rectifier. I looked up as best I could for that rectifier, and I thought it was about 1.1 volts DC voltage drop across each internal diode, which would have been 2.2 volts DC drop, which would have given us from 120 to 118 volts RMS, and at a frequency of 120. Turns out, here's the formulas, by the way, VI up here, and this is RMS, minus 2 times the voltage drop across the diode. This is across a single diode, this is across two, because you're always passing across two diodes on either side of the bridge. And then the frequency is just the initial frequency times 2. And so what we actually measured on the downside of that, on the outlet side of that rectifier, was more like 115 volts, which sounds to me that this 1.1 volt DC that I came up with was underestimated, but that's fine. So we go back now. In order to get rid of that ridiculous ripple, that is ridiculous ripple, 0 to 170-ish volts, to get rid of that ripple, we want to add capacitors to the system. Capacitors act as reservoirs for charge. So what happens is, when the voltage is going to be high, these reservoirs are going to fill, and then when the voltage drops, these reservoirs are going to deplete. They're not even going to deplete, they're going to discharge, and that's going to take that ripple way down. So you got to figure out how far down you want the ripple, and then you can calculate what your goal is for ripple. Then you can calculate the actual capacitance required. So in this case, we estimated 1.4 amps for the draw of all banks in the light, and we set our duty cycle for the capacitor is about 70%. What's the duty cycle? The duty cycle is that part of the cycle which the capacitor will be discharging. So if it's discharging 90%, you're going to need a lot more capacitance than if it's discharging 30%. In our case, if you look at a typical curve, or my estimation and others, you can expect about 70% duty cycle. So we'll go with that. I have 1,000 microfarad capacitors, which I showed you. So that's what we're actually going to try to use. How much ripple are we willing to take? Well, I just pulled a number out of the air. I said the peak-to-peak ripple value voltage I'd like to not exceed 4 volts, which gives us a ripple in percentage of 2%. It's 2% ripple, and that's pretty darn low. And that's measured by the voltage of the ripple, which is 4 volts. The allowable ripple voltage divided by the frequency, which is 120, times 100, which takes you to percent, and that's 2%. Then, I'm going to estimate the actual voltage, the final voltage. Again, we have to go from an RMS value, which originally I calculated 118, maybe a bit higher, or lower rather. But take that 118 volts, multiply by square root of 2, and then we're going to end up with about 167 volts DC current, with about a 4 volt ripple, or about a 2% ripple, assuming we used a 2,000 microfarad capacitor. We calculate that by saying the current, final current, 1.4 volts, times the duty cycle, 70%, times a million, which this equation is typically in farad, and we're going to test it in microfarad, so that converts us to microfarad, divided by your ripple voltage, 4 volts, divided by the frequency, the final frequency, the frequency at the rectifier, it's 120 hertz. You do all the sums, and you get 2,042 microfarad. Again, I don't have a 2,042 microfarad capacitor, but what I do know is if I put capacitors in parallel, those microfarad ratings, or those farad ratings, become additive. So if I use 2 of these 1,000 microfarad capacitors in parallel, I'm going to have 2,000 microfarad, and that's exactly what I want. So, well, close enough to exactly what I want. If this is 2,000 and we need 2,042, just means our ripple is going to go up ever so slightly. It's way more than adequate. So I actually did it and hooked it up, and this is what I measured. My line sample was about 122.5 volts AC. Without a load, excuse me, without a load, the DC voltage was 165 volts DC. So the only thing you have there is the loss of voltage due to the diodes in the rectifier. And then when you turn on when you actually turn on the fixture, you get a new RMS, which is 160, or new, measured RMS voltage is 162 volts. And that's just saying that we have a ripple that's around 3 volts, 4 volts, which is exactly what we calculated. Excuse me. Which is exactly what we calculated. So, pretty happy. This is how the calculations go. This is the theory behind the circuit. This is what sine wave for normal AC current looks like. This is it after rectification. I didn't draw it. But then there's a whole other curve, very small, that occurs after you put in the capacitance to stabilize the ripple. So let's move on and see how this thing turns out. Alright, so as we get ready to plug this in, I just want to make a comment. Right now you'll see that over here I've got this hooked up with some test leads. Be very careful. That's a lot of capacitance. 2000 microfarads holds a lot of energy. You plug this in, you charge it up, and then if you unplug it, and I'll show you what happens when you unplug it, it will bleed some of that voltage down. But there's still the potential for stored voltage in those capacitors, not even potential, reality. And so if you go and toy with that too much when it's got that stored energy in those capacitors, it could bite you. So just be aware. You can discharge those capacitors by simply jumping across the wire. Once it's unplugged, you can jump 2 wires and it'll discharge, or you can leave it plugged in for enough length of time potentially that it will ultimately discharge through the circuitry and the LEDs. But understand, it may actually bottom out and not remove any more stored electricity, and you can still have some stored in there. So be careful. Capacitors can bite you. Let's plug this thing in. There you go. So, blinding, it's quite bright. I did try to take some pictures. No, that's not true. I did take pictures. I took pictures of it in 3 different modes, with 120 volts AC, with the 120 volts DC, once rectified but not stabilized, still had ripple from 0 to 160 some volts, and then took a picture of it in the mode you see right now, which is once it has stabilized at roughly 2% ripple and 165 volts, and the difference is dramatic. Regretfully though, when I took the pictures, I didn't think about the fact the camera was just going to adjust for the peak light. So basically every one of them looks very much the same, because the camera adjusted its shutter speed to accommodate. So bottom line, this thing produces a ton of light. Whether I use this as a single unit, whether I use this thing as a series of light bars, I think it'd be very interesting actually. Used to raise coral in saltwater aquarium. Lighting's critical for coral. I'm not sure about the frequency of this light, whether it's how well it represents sunlight, but if it represented it well, these would make some pretty neat light modules individually built into a light bar for a coral or other type fish tank. But I don't know what we're going to do with it yet. We're just going to play with it, and we did, and we love it. It's fun. You get your hands on a street light, you might find it useful. Be sure and check your circuitry. Make sure that you understand what your requirements are. In my case, with that LED light driver and that I was able to take out of there and able to get right to the actual wires going to the bars, light bars, I was very much able to understand what voltage, what amperage would work the best. This could be turned up. I think that thing said max 250 volts DC output on the electronic driver, so I assume these things could handle that level of DC voltage. In our case, we're only at 165, but hey, it's ridiculously bright enough without having to go to that extreme. So remember that 165 volt DC rectified from 120 volt AC. Could potentially drive LEDs for you. Double check all your LEDs, make sure that they don't already have drivers built in. A lot of like the LED fluorescent tube replacements, they have built-in drivers that convert to power. They basically have rectifiers built into them. And so, yeah, it's not a given that this voltage or this amperage, this DC versus AC is what you need. In this case, by doing some research on the light, we were able to determine that this was correct. Nifty, fun, maybe boring to you, but I entertain myself with such silliness as this. Y'all take care. Have a good day. Later.